Welcome back for week 4 here on Radio 146, your favorite station for all the greatest remote sensing hits. DJ David at your service this time around, coming at you to discuss the issues of perspective and resolution in digital imagery analysis. So the traditional digital mapping world of GIS consists of points, lines, and polygons, all tools that are helpful for things like navigation and delineating political boundaries. However, GIS vector data does very little in the way of allowing a user to visualize and analyze geographic features as they exist on the ground, so to speak. This is where remote sensing goes above and beyond, providing us with both visual and non-visual data of the landscape or feature of interest. Now, remote sensing, and well, life for that matter, is really all about perspective. The information we are able to ascertain from an image is profoundly influenced by things like our field of view and the context in which we relate objects to their surroundings. Not to mention myriad sources of error like image distortion, atmospheric haze, low light levels, and on and on. But the important takeaway here is that how you view an image matters greatly in its interpretation. Sound clear as mud? Well, let's look at a few fun examples to emphasize the importance of field of view and context before diving off the deep end into resolution. So what are we seeing here? A crazy celestial body? A terribly discolored egg? Let's zoom out a bit. Well, clearly it looks like an eye now. So context tells us we're looking at an animal. Can you use anything around the eye to help you guess what type of animal it is? What do you think these green and purple things are? And can you tell by the texture? If you guessed feathers, you are correct. It's a winged dinosaur. This is a New Zealand bellbird. Perspective is inherently linked to resolution. Our ability to analyze and interpret imagery is largely a function of its resolution properties, of which there are 4 major types. Spatial resolution, which we've delved into quite a bit in lab already. Spatial resolution in remote sensing mainly refers to the pixel size and coverage of an image. Then there's spectral resolution, which refers to the number of bands an image contains that delineate unique portions of the electromagnetic spectrum. Next is radiometric resolution, which refers to the ability of a sensor to detect subtle differences in brightness, or in other words, its sensitivity to the energy reflectance or emissivity of landscape features. And finally, and arguably the easiest to comprehend, temporal resolution simply refers to the frequency with which an image is captured over time. For example, Landsat images are captured once every 16 days in the same location, which might be considered moderate temporal resolution. Then, a sensor that captures imagery daily would have a high temporal resolution. Okay, so focusing in on spatial resolution now. You should already know that spatial resolution refers to the area on the ground represented by a pixel. So, for example, an image with 2-meter resolution would have a pixel size of 2 meters by 2 meters and hence represent 4 square meters on the ground. Remember, we're talking area here. Now, where it can get a bit muddled in your head is low spatial resolution equates to large pixel size, and vice versa. And remember, resolution is relative. Inherent to every sensor, there is a limitation on how small an object on the Earth's surface can be perceived by the sensor as being separate from its surroundings. Now you may be thinking to yourself, well, why don't we always use the highest resolution imagery possible? Because high res is great. Sure it is, but there are several important trade-offs to consider when deciding what type of imagery to use for your objectives. First, image footprint, or how much land the image covers. Covering a massive amount of area is nice, but it comes at the cost of reduced spatial resolution, or higher pixel size. Similarly, covering a lot of ground, as from a satellite platform, also introduces a lot of image noise and error. Cloud cover, like we see in this Landsat image, for example. Processing time is another major consideration. How much time is it going to take to get an image or many images to the point where you can analyze them? For example, satellite imagery is going to require some additional atmospheric and geometric corrections, which we'll get into later in class, since it was acquired from space. And aerial imagery, on the other hand, is going to require a lot of mosaicing to cover a reasonable spatial extent. The next 2 trade-offs are arguably the biggest limitations on the use of high resolution imagery today. High-res images cost a lot to produce. Flying planes ain't cheap, and hence they typically are not free to the user. And due to the sheer number of pixels they contain, they also result in massive file sizes that can burden the storage capacity of most computers. Nonetheless, it's important to note the information lost with decreasing spatial resolution. So focus your attention on this Landsat image, and I'm going to show you a series of images that cover the same area but at decreasing spatial resolution. Now this is MODIS, another satellite, but at 250 meter resolution, 500 meter resolution, and another satellite, AVHRR, at 1,000 meters resolution. The major takeaway here really is that you need to match your spatial resolution to your objectives, considering all of these trade-offs. For example, if you're doing a global study, perhaps this 1,000 meter resolution is your best bet, considering processing time and footprint. Whereas if you were focused solely on Vermont, you could probably get away with using the Landsat 30 meter resolution imagery. To highlight the trade-off between spatial resolution or pixel size and image footprint or scene size, have a look at these two images here, where you can see something like QuickBird, which has a 2.4 meter pixel size, only has an 11 kilometer by 11 kilometer image footprint. Contrast that to Landsat, for example, which has 30 meter by 30 meter pixel size and covers 185 kilometers by 185 kilometers. Much, much bigger spatial extent, but at the cost of increased pixel size. Okay, so now it's time to don your analyst cap and answer a few image resolution scenarios given the trade-offs I just discussed. So if your goal is to map urban forests, including individual street trees, which is the ideal resolution to use? If your goal is to map impervious surfaces, including buildings and driveways, which is the ideal resolution to use? The general rule of thumb when trying to identify target features on the landscape is that your imagery's pixel size should be at least 1/4 of the feature size that you are trying to identify. For example, here, if you are being creepy and hoping to identify people's vehicles in a lot, you would need imagery that has at least 4 pixels for a given vehicle. Clearly, the resolution shown here is sufficient as the truck is comprised of many pixels. Let's look at another example. So here we have a 20 meter by 20 meter house right in the middle of 20 meter by 20 meter pixels. So when we classify this, or if we try to identify the house on the landscape, we are not going to be able to. And that's because the house only makes up a small portion of the values contained in these pixels. However, if we have 5 meter by 5 meter pixels now, here, you can see that the middle 4 pixels here are comprised almost solely of the house. And so when we do a classification, you will see the house detected in those middle 4 pixels. So take about a minute here and go through these 3 very realistic yet very depressing scenarios in which you are trying to match your ideal pixel size or spatial resolution of your imagery to the feature you are trying to identify on the landscape. So what is your ideal pixel size for roadside bombs along a military supply route if the estimated bomb size is about 50 centimeters? Well, 1/4 of that is approximately 10 centimeters, a little more. So you'd want 10 centimeter resolution imagery. How about 10 meter wide logging roads in Mount Hood National Forest? Well, about 1/4 of that is 2.5 meter pixel size or spatial resolution. And finally, deforestation across the entire Amazon, considering clear cuts are approximately 1 kilometer wide, which is super sad. You'd want approximately 250 meter resolution imagery. So you could get away with using something like MODIS satellite image that we saw earlier. Shifting gears a bit here now, want to discuss one of the major issues faced by remote sensing analysts especially when using lower spatial resolution imagery, and that's the mixed pixel effect. As your spatial resolution decreases or your pixel size increases, brightness values are averaged over larger and larger areas, and so they contain more and more different land cover types. For example, if you look at the image below and imagine that being a very large pixel, you've got a tree, some shrubs, bare ground, rocks. So you've got a lot of different spectra represented in your reflectance curves. Land cover classification is also largely a function of contrast. So if there's a strong contrast between an object and its surroundings, that object will manifest even in large pixels. For example, if you look at this image here and our pixels, you've got strong contrast between these roads and the vegetation and then these darker shadow areas, which will then manifest when we classify those pixels. In an ideal world, you would have unique spectral signatures for all of your target pixels or target features that you're trying to classify. Alas, that's almost never going to be the case, as regardless of what resolution you're at, even very high resolution imagery, you're almost always going to have some mixture within your pixels. Imagine your task is to map forest cover over this large area. With our smallest pixel size here, you can see we're getting a lot of pure forest pixels here on the left and the bottom right hand corner, but we're also losing quite a bit of forest in chunks here to a mixed pixel. Here we lose some. Pretty much anywhere where we have a different land cover type mixing with forest, especially with a large contrast, you're going to get a mixed pixel classification. Moving over here to more of a moderate pixel size, you can see that we pretty much are all mixed now. We've only retained two forested pixels, which are almost 90 to 95% forested. And finally, in our largest pixel size here, it's simply classified as mixed. You have multiple land cover types here contributing to the overall spectral characteristics, which would no longer be, with your brightness values averaged over these land cover types, would no longer be considered classified as forest. Sort of on the flip side of this issue of mixed pixels is that you can have imagery that has too high of resolution when you're classifying a landscape. For example, in the fields you can also see sort of these different colored patches within there. The field may by and large be similar, but you're going to get these small patches where you have a completely different classification. For example, you have some forested pixels right in the middle of the field, perhaps a few barren land here and here, and that's because those particular pixels had spectral characteristics similar to what the forested areas were, or the barren land areas over here. The river has some exposed areas and then the deeper water, but it also has trees overhanging it, so you're going to get some mixed pixels with not only water or sandbar but also some vegetation. And if you look closely here at the classification, it really struggles with it. You even have some urban areas up here where this particular exposed area was more similar to, say, the roads over here. Very little of it is actually considered just plain water, when clearly that's a river. So where our low spatial resolution imagery was having the problem of overgeneralizing the landscape with mixed pixels, we're sort of seeing the opposite, where the high resolution imagery is seeing too much spectral difference in its mixed pixels when it should be perhaps generalizing more. Coming full circle here, like we mentioned earlier, most pixels are going to be mixed pixels regardless of what type of imagery you're using. So how can we still complete remote sensing objectives given this issue? Well, remote sensing is still particularly adept at classifying large homogeneous areas, or areas where your spectral signatures are very similar, such as focusing solely on forests or solely on oceans, agricultural fields, etc. And even in heterogeneous areas, the mixture can often be similar. And there are also some special algorithms out there that can actually unmix mixed pixels, or classify at a subpixel level. One example being this particularly near and dear to my heart algorithm called Spectral Unmixing. We'll talk about this more in depth as the semester wears on, but part of my PhD research is using this Spectral Unmixing algorithm to classify tree species using Landsat imagery. So 30 meter by 30 meter pixel, trying to pluck out what components of that 30 meter pixel are actually a particular species. So in order to do that, you have to train this algorithm or the classifier on a pixel of pure spectra for whatever material you're interested in. So let's say we're trying to map sugar maple. We need pixels where we know sugar maple is the only species there. And then we can use that spectral signature to examine each pixel across the landscape and quantify how much of a given pixel contains sugar maple. So for example, pixel X contains 20% sugar maple, whereas most classifiers would say it's either sugar maple or it's not. Another method that is used to overcome the mixed pixel problem is object-based classification. Object-based classification begins by first segmenting the image into larger polygons by combining like pixels. So if you look at this high resolution image on the left, you know it's made up of thousands, perhaps millions of small pixels, but if you look over here on the right, the classification is actually being carried out on these larger polygons. Now these polygons are basically pixels that are grouped based on an array of user-defined features. Things like spectral characteristics, texture, color, shape, and more can all be used to segment into these larger polygons. Now where object-based image analysis, or OBIA as it's commonly referred to, is particularly useful is in overcoming the misclassification errors we explored earlier with high-resolution imagery. By combining similar areas into polygons before classifying, OBIA avoids the big field with randomly misclassified forest pixels in the middle of it. Finally, shifting gears to spectral resolution. Spectral resolution refers to the specific wavelength intervals on the electromagnetic spectrum that a sensor can record, both in terms of the number of spectral locations as well as the width of each spectral band. Note that some sensors have many narrow bands only in one or two regions, where other sensors have wider band intervals but cover the visible, infrared, and thermal portions of the spectrum. A couple examples down here, lower spectral resolution, so wide wavelength intervals and or fewer bands. Panchromatic is as low as you're going to get, just black and white over a single band. Then there's multispectral, where you have most multispectral sensors these days cover the visible portion as well as near infrared. Landsat is multispectral. It also covers portions of the thermal and mid-infrared. But really, these examples are low resolution when compared to the higher resolution hyperspectral imagery, which can have upwards of 100 or more narrow spectral bands. And just to highlight this visually, here's a spectral reflectance curve for grass in relation to these different forms of imagery or sensors. One band panchromatic, black and white imagery, so one uniform reflectance over the visible portion for grass. Your 3 to 4 band aerial imagery that we've looked at in class, which covers the visible portion but also contains a near infrared band, which you can see for grass. Obviously green is going to be reflected quite a bit, but look at the near infrared reflectance. That's why this near infrared band is so important for delineating or classifying vegetation areas. Contrast those to this high spectral resolution hyperspectral data, which covers the same wavelength interval, but look at all those bands. Hoo-wee! Think of the utility of having so much spectral data available. Rather than simply identifying grassy areas, for example, you could be classifying types of grass in an image. A couple important points here though. There is no magical sensor that records all wavelengths. They all have limits to their capabilities. So much like spatial resolution, it really comes back to trade-offs and what works best for what your application is. For example, imagery with visual and near-infrared bands is readily accessible these days. So if those are the only bands you need, then the next logical step is finding the right spatial resolution. However, if you're trying to discriminate, let's say, types of vegetation across a large heterogeneous landscape, while the near-infrared band certainly helps, it is by no means sensitive enough to pick up very subtle differences. That's when an example of when you would want to start looking for better spectral resolution. Again, there are some important trade-offs to consider. There are some clear advantages we just went over, like the numerous spectral bands and narrow bandwidths, which provide a massive amount of spectral data. That spectral data then enables us to discriminate some very subtle features on the landscape, since each feature is more likely to have spectrally distinct or pure pixels. This is why hyperspectral imagery and its analysis is used in some heavy fields like defense and oil, gas, and mining operations. There are also a wealth of analytical techniques out there for hyperspectral data, much more so than for traditional 3, 4, or 7 band imagery. That said, it's not all roses here, folks. The data is certainly complex and thus requires a high level of expertise. For example, if you have a question about hyperspectral data, ask Jen, not me. It is also costly to acquire, both in the air and on the ground for the user. So again, there's a reason many hyperspectral applications today are defense or mineral exploration related. They have the funds. Hyperspectral sensors also only cover a small area with each pass and still produce some pretty massive data files. So if you don't have a supercomputer or are working off of a cloud server, chances are high that you won't be able to store, much less analyze, many hyperspectral images. And finally, there's this issue of accuracy. How do we confirm what the hyperspectral sensors are detecting in the air is actually what's true on the ground? Similarly, will the spectral signature of a material mapped in Vermont, say, be the same as the same material mapped in New York? Think trees, for example. Will a stand of sugar maple mapped as pure in Vermont look the same or have the same spectral signature as a stand of pure sugar maple in New York? Zooming back out a bit here again, how are spectral bands for a sensor selected in the first place? Well, it all has to do with what are called atmospheric windows. They are called windows because they let energy in from space all the way to the Earth's surface. So if you look at the y-axis, you'll see percent atmospheric transition from 0 to 100. Sometimes this is just called transmissivity. If you focus on the latter portion of the UV wavelength through the visible colors, you see nearly 100% atmospheric transmission, meaning these energy wavelengths radiate to the Earth's surface relatively unimpeded. They go through the window. The troughs are caused by greenhouse gases that either absorb, scatter, or reflect incoming radiation before it reaches the Earth's surface. So for example, ozone here, O3, absorbs a significant portion of the UV wavelength, which prevents the human race from instantaneous global skin cancer. Just kidding, kind of. Obviously, band selection is a major important piece to consider when you're trying to map a material of interest. Looking at differences from peak to trough can often help discriminate vegetation features on the landscape. And finally, just wanted to provide you with a general overview of some of the sensors and their spectral bands so you can compare them. Obviously, the higher resolution imagery tends to not have any of the mid-infrared or thermal imaging. And then as you move down, I want to make an important note here, and that this figure is a little bit dated. Landsat, this is Landsat 4 and 5 thematic mapper. Since then, there's been the Landsat 7 enhanced thematic mapper, which added one more mid-infrared band, and now Landsat 8, which added another band at the edge of the blue called ultra blue, which is supposed to be useful for coastal or aerosol studies. And then they also added another thermal imaging band. Alrighty, now for our third and likely shortest section on resolution, radiometric resolution. So radiometric resolution refers to the sensitivity of a sensor to perceive very slight differences in energy levels or brightness value levels, and is described as the depth of the digital number, or which is also known as its dynamic range. Imagery data are always represented as positive digital numbers, which vary from 0 to a selected power of 2. Each bit is a selected power of 2. So 1-bit data, for example, would be 2 to the power of 1, or 2 possible values. So it's binary, 0 or 1. 4-bit data, on the other hand, would be 2 to the power of 4 possible values, or 16 possible values. So 0 is always included in that. So it's not going to be 1 to 16. It's always going to be your 16 possible values is going to be 0 to 15. 0 would always be included in that. And 8-bit data, 2 to the power of 8, 256 values, which is 0 to 255, and on and on. And the higher number of possible values you have that can be stored is the higher your radiometric resolution. So to give you another way to visualize this in terms of why it really matters, you have two sensors here that have the same exact spatial resolution, the same spectral resolution, but a different radiometric resolution. So sensor A can record 256 different intensity levels, so it's 8-bit data, whereas sensor B is only 2-bit data and can only record 4 intensity levels. And just look at the difference in the image displays here. Well, so why don't we just make all sensors as high a bit depth as possible? I'm guessing by now you realize it's due to what? Trade-offs! It's basically a three-way juggle for a sensor between spectral resolution, spatial resolution, and radiometric resolution. My friends, we have reached the final section. So the fourth consideration for any remote sensing system or sensor is temporal resolution, or the frequency with which it passes over the exact same spot. This is also known as its revisit time. Now, temporal resolution is really a major consideration when one is concerned with areas that have persistent cloud cover, like the tropics. I personally added New England here due to my own loathsome experience with clouds in the Northeast. There are literally 4-year periods in the Landsat archive where not a single image exists over Vermont with less than 10% cloud cover. Now, natural disaster mapping and other short-lived phenomena also require reasonable temporal resolution for before and after analyses or to identify areas in need of relief. Just wanted to briefly mention that the SAL lab here at UVM has a really cool disaster risk mapping team you should check out. And this is another area where mobile deployment of remote sensing systems is becoming increasingly useful. And finally, any research or objective that requires the comparison of multiple image dates obviously benefits from increased temporal resolution. There are certainly instances where 2 image dates are all that is needed. For example, if you're looking at development around a city, for example, here's stores around Yukon. You have 1 image date in 1999. If you focus your attention on these areas, you'll see that in 2002 there were some pretty drastic changes. And so you could quantify in that 3-year time period, for example, how much forest land was lost due to development. Sometimes you need images in a much more rapid succession. So here's the breaking off of the Isles ice shelf. This is all over the span of 1 day, mind you, August 13th, 2005. Focusing your attention on where the red arrow is, you can see it's slowly calving and then completely breaking off. Unfortunately, those scenes will probably be more frequent in the near future. Now, I've already mentioned Landsat multiple times in the context of revisit time, but just in order for you to visualize it here on the right, that's the sort of orbit path. But for many sensors, it's much more complicated than that, just that 16-day revisit time. Some sensors have the ability to point, so I mentioned there are sensors out there where the temporal resolution is on the order of 1 to 5 days. That's because if you have the ability to point, you can image the same spot more often than if you are not able to point. Another thing that affects temporal resolution of a sensor is latitude. Sensors that have a polar orbit will have overlap of paths at higher latitudes, so those higher latitudes will get more frequent revisits than lower latitudes. With temporal resolution, it's really again a matter of choosing the sensor and thus the imagery that fits your objectives. If you need a high temporal resolution, obviously you might want to look at satellites. If you need high resolution imagery and not a lot of temporal resolution, perhaps you look at aerial imagery, for example. Okay, now you should be familiar with the 4 different types of remote sensing resolution. You should know that all of them are important considerations in sensor design, and that really that trade-off between the four defines the utility of the sensor for a given purpose. And as a remote sensing analyst and student right now, you should be able to match your resolution needs to whatever application you're using it for, with the caveat that there really is no one size fits all when it comes to sensor design and hence imagery. I'm giving you here a Vermont DOQ, which is an aerial photograph, an Icono satellite image, and then a Landsat satellite image. And we've listed the resolution, different forms of resolution for each. So which of these, in the first scenario, which of these would you use to map algal blooms in Lake Champlain for water advisory decision support? Well, by process of elimination is how I like to do things. So right away I would eliminate the Vermont DOQ because it only has one band and you're not going to be able to see algal blooms in water with only one band. So we're really between the Iconos and the Landsat imagery. One thing that jumps out right away is the difference in resolution. Okay, but maybe in Lake Champlain we're not as concerned about that, though it does play a factor. For me, what it's really about is can we see algal blooms with both? I think so. Having the near infrared band really helps. So we'd be looking basically for vegetation floating on water, which we should be able to get from the NIR band in both of these, or in worst case scenario, derive a normalized difference vegetation index from both of these. I think what concerns me the most would be the temporal resolution. So Landsat image every 16 days, perhaps the algal bloom is relatively short-lived, or cloud cover affects our Landsat imagery over the summer, and thus we're really stuck between a rock and a hard place in terms of being able to tell changes over time. So I would lean towards using the Iconos here with the 3 to 4 day return interval. Okay, so last one I'll help you with here is which of these would you use to map structures for town tax assessments? So again, process of elimination right away, 30-meter resolution for Landsat. You're not really going to be able to tell structures with that, even if you do have more spatial spectral resolution. I'm sorry. So between Iconos and the Vermont DOQ here, 4-meter resolution, you should still be able to see a lot of structures, but they're going to have to be relatively big. You don't necessarily need the 4 bands, and the return interval really for a tax assessment isn't going to matter. So that's where I would go with the DOQ here, because one, the very high spatial resolution. You don't have to worry about it only being one band because you can still see structures given that spatial resolution, and it's on demand, so you really would only need it once in the year. Okay, for the last 3 you're on your own. I'll put them on the screen here and you can scroll back and forth. So the next one deals with forest decline. Then you're going to concern yourself with land use change, and finally fall phenology timing. Best of luck, and we made it through.